Hello everyone. In this video, we will go over Chapter 12 of the lab manual, which is the F-test for equality of two variances. We usually just call this the F-test, and while this chapter describes the F-test as a standalone test, it's important to note that this test is rarely used alone. It is almost always used in conjunction with a two-sample t-test, which I'll discuss in a future video. As always, here's a slide on what is reviewed in this chapter, and we'll go through each one of these. The F-test is only used to test variances. It is not used for any other statistics. It is also called the variance ratio test because it calculates the ratio of two variances. It relies on a normal distribution. So the sample or the population being tested must be normally distributed. For this class, you don't need to worry about that. It's just something you may need to know for a conceptual question on a lecture exam. For the F-test, we may have homogeneous or homoscedastic variances, and this means that the two variances being compared are close to equal, so that final ratio will be close to 1. On the other hand, the variances may not be close to 1, and therefore they are heterogeneous or heteroscedastic variances. This would mean their F-test ratio would be greater than 1 or less than 1. The F distribution is a little bit different than distributions we have seen so far. It has a positive skew to the right, which you can see in this picture here. And the shape of this distribution is dependent on the degrees of freedom of the two samples we're comparing. Here you can see if the 2 degrees of freedom are 1, we have a very skewed distribution. The next one we can look at is this blue one, which increases the degrees of freedom, to 5 and 4. And then the final one, this kind of gold one, the degrees of freedom are both 10 and 20. So the skew is pulled a little bit out here and the shape greatly changes. And we'll see how that affects the critical values in just a second. I always like to provide a summary method slide for how to do these tests. Again, the F-test is primarily used as a pre-test for two-sample t-tests, which we'll see in the next video. But in this chapter, we will just look at it as a standalone test. The summarized methods are to, as always, write out the hypotheses, choose the level of significance, and then slightly different, now we're going to calculate the F value or F calc. Then we'll find F crit using the degrees of freedom to either look them up in the F table or we can use Excel. Just like with a t-test, we'll compare the calculated and critical values, we'll find the p-value, and we'll make a statistical conclusion. For standalone F-tests, you can also come to a biological conclusion, but in this lab, we will only be using the F-test as a pre-test for other statistical tests. Let's break down each one of these steps. Step 1, write out the hypotheses, the same as any other statistical test. For a two-tailed hypothesis, now we are comparing variances, represented here with sigma squared. For a two-tailed, this means the null would be that our variance of the first sample is equal to the variance of the second sample, the alternative being that those variances are not equal. For a one-tailed hypothesis, left or right, we have the exact same types of null and alternative hypotheses, but now we are comparing variances. If you have questions on how to write these hypotheses, please review the one sample t-test video. Step 2, level of significance, almost always 0.05, and it will be given. Step 3 is to calculate that F calc value. And what you'll notice here is these two equations are almost identical. The only difference is for the one-tailed, we use the word predicted. Because in a one-tailed hypothesis, we have a sample group that we are interested in if it is larger or smaller than the other sample group. The takeaway from this slide is for the F-test, the larger variance always goes in the numerator of this test. This will mean that the F-calc value is always positive, so you can always use the right tail value in the distribution. Remember, this distribution is not symmetrical, so by doing this, we avoid any issues that may occur by finding the left tail of this distribution. Again, the takeaway from this slide is to always put the larger variance in the numerator of the F-calc ratio. The fourth step in the list is to find the F-crit value. There's two ways to do this. The first is to use the F table. There are multiple F tables for different alphas, so be sure you look at the top right of the table to find which alpha value you are currently using. This example is for alpha at 0.05. If you are using a two-tailed test, you need to use the F table for alpha over 2. So if alpha for your general F test is 0.05, when you go to the table, you need to use 0.025. But for a one-tailed test, which we should be using anyway, we'll just stick with alpha. We don't have to split it between two tails. To read this table, we will use the first column with the degrees of freedom of the denominator, and the row is the degrees of freedom of the numerator. This body, highlighted here in gold, is the F-crit value. Similar to the t-test, the next steps will be to compare the calculated and critical values and to determine the p-value. We can determine the p-value in Excel or in R, and I will discuss both of those in this video. The last step is to make your statistical conclusion. Since we are always putting the larger variance in the numerator, if F-calc is greater than F-crit, we reject the null hypothesis. If it is less than F-crit, we do not reject or we accept the null hypothesis. Again, in this chapter, we will also make a biological conclusion, but in general, there is only a statistical because this F-test is used as a pre-test. Here is a summary of the commands we can use in Excel to complete the F-test. F-calc is always going to have the larger variance in the numerator and the smaller variance in the denominator. To find the critical value, we'll use a new function, f.inv.rt. For a two-tailed, we will divide alpha by 2. For a one-tailed, we will just use alpha. Then we will use the degrees of freedom of the numerator and the degrees of freedom of the denominator. That's notated here with this V symbol. It's the Greek letter nu, and I will just say degrees of freedom, but know that's what that stands for. For the p-value, we will use f.dis.rt. For a two-tailed, we must multiply this by 2 because we were using alpha divided by 2. The arguments are the F-calc value you found up here, and then the degrees of freedom of the numerator and denominator. Similar for a one-tailed, but we do not multiply by 2. That is the end of these slides, so let's go ahead and open Excel, and I'm opening the Chapter 12 Excel template. These problems come from your lab manual on page 125. The first question has a table of body weight in terms of percentage deviation from the ideal body weight. Group 1 is healthy patients and their deviations. Group 2 are cancer patients and their deviations. And the question asks us to use a statistical test to determine whether the variability in these body weight percentages are the same for the two groups. This data is copied here. And I'm going to zoom in just a little bit. And as always, we'll start with our hypotheses. This is going to be a two-tailed test because we are only interested in if there is a difference. The direction does not matter. Because of that, our null hypothesis will be that the variance of group 1 is equal to the variance of group 2. The alternative hypothesis is that the variance of group 1 does not equal the variance of group 2. And I'm going to go ahead and insert that symbol just so it's super clear on here. You could also represent these with sigma squared, but I don't want to spend time inserting that symbol in the squared. So we'll just use var1 and var2. We're going to use an alpha of 0.05 for this problem. And the first thing we need to do is figure out what F-calc is. F-calc uses the variances of the groups. So the first thing I'll find is var1. Calculating that, we'll use the var.s function, which we're very familiar with. Select only the samples from the healthy group, and we get 0.145. The unit here, as a reminder for variance, is going to be deviation squared. Variance units are squared. Standard deviation units are not squared, which is why we use standard deviation to compare values more than variance. Now we'll find the variance of the second group. We'll also use var.s. We'll select all the data from this second group, and the unit is again deviation squared. This gives us enough information to start the F-test, which I've put in a different table down here. The first thing we'll calculate is the F-value, which is also called the F-calc value. The F-calc value is calculated by putting the larger variance over the smaller variance. This will always be the case. So we're going to say equals the larger of these two variances, 0.348, divided by the smaller of these two variances, 0.145, and that's it. That gives us our F-calc value. The next thing we want to find is the critical F value, also called F-crit. To do that, we need to find the degrees of freedom of our numerator and denominator. What becomes very important here is being consistent with your labels of the groups. So in this example, I have called var1, associated it with the healthy group. var2 is associated with the cancer group. So I need to keep using that notation in order to be consistent and get the correct answer. First, I will find the degrees of freedom 1. To do this, we can use the count function, select our data, close the parentheses, and subtract 1. Degrees of freedom 2, we'll do the same thing with the cancer group data, minus 1. So we have 9 and 15. Again, this is very important, keeping track of which number was the numerator and denominator. For the F-crit value, we are going to use a new function, f.inv.rt. You will always use the .rt function. For a two-tailed problem, we will use alpha divided by 2. For the probability, alpha is 0.05 divided by 2, or you can type in 0.025. Degrees of freedom 1 is the degrees of freedom of the numerator. The numerator we used was var2. So the first argument for the critical F value will be the second degrees of freedom we found. The degrees of freedom 2 is the degrees of freedom of the denominator. The denominator of our F-calc value was from group 1, so we will use degrees of freedom 1. That will give us 3.769. The next step is to find the p-value. To find the p-value, we're going to use the function f.dis.rt. Again, we're always using the .rt function for the f-test. The first argument is the f-calc value. And again, we have the same thing with degrees of freedom. The first degrees of freedom for this function is the numerator degrees of freedom, and the second is the denominator degrees of freedom. For a two-tailed f-test, we need to multiply the p-value by 2 to restore what our original alpha was. And we get a p-value of 0.187. When we compare the f-calc value to the f-crit value, we see that f-calc is less than f-crit. This tells us to accept the null hypothesis. The f-calc value is not more extreme than the crit value. When we look at the p-value is greater than alpha. Alpha was 0.05. This also tells us to accept the null hypothesis. That is our statistical conclusion. Accept null hypothesis. This question was a standalone f-test, so it does require a biological conclusion. Again, in this lab, we will only be using the f-test as a pre-test, but to get us used to talking about biological conclusions, we'll go ahead and do that here. So since we accepted the null, let's look at the null again. The null says the two variances are equal. The question asked us, use a test to determine whether the variability are the same. Have we answered that question? We have. So we can say the percentage deviations in body weight are not different, i.e. are the same, for healthy patients and cancer patients. Again, biological conclusions do not have to be very long. As long as you convey that you understand the concept here, that is sufficient for the biological conclusion. And that is it for the f-test. We are going to do one more. I'll go a little bit faster the second time, and then we're going to go into R. So I'm going to move over here to question 2. Question 2 is also from page 125. And in this question, we have a fish called the black surf perch, and this occurs together with another fish called the striped surf perch. That is a hard word to say. This researcher is interested in if the co-occurrence of these fish affected the variability in the length of the black surf perch. And if so, the decreased variability would mean there's some competitive interaction in this ecology interest. So this question asks us to determine whether these variances differ in the suspected direction, that being that decreased variability direction. Let's go ahead and look at that in Excel. We have our same given data. In this example, the interest is in if there is a decrease in the variability. This would mean we want to perform a left-tailed test. Remember, with hypotheses, it's usually easier to start by writing the alternative hypotheses because it matches the direction of our test. So in this example, for our alternative hypotheses, we'll say var1 is less than for a left-tailed test, var2. For the null, we can say var1, we want to write the complementary hypothesis to the alternative, so we will use greater than or equal to. Remember, the equal sign always goes in the null. So var1 is greater than or equal to var2. The rest of the test is performed the same. So I'll go ahead and calculate var1, var2, degrees of freedom 1 and degrees of freedom 2. And just again, as a reminder, the units here, these are weights, they are lengths, and we will say the unit for variance, just as a reminder, is length squared. There are no units for degrees of freedom unless you would like to write fish. F-test, first thing I'll do is find the F value, and I'm going to copy this information from the first problem. Again, for the F-calc, we always put the larger variance in the numerator. In this problem, again, our larger variance came from the second group, so we'll do larger variance divided by smaller variance. To find the critical value, we can use the table. So let's go ahead and look at that for this problem. Here is the table of critical values for alpha equals 0.05. Since this is a one-tailed test, we will stay in the 0.05 table because we do not need to divide alpha by 2. Looking at our degrees of freedom, we have for the numerator 37, for the denominator 29. Let's see if that's on here. And unfortunately, it isn't. So the F table only goes so far, just like we've seen in other problems and other tests, but that's okay, because we have our f.inv function. So we'll use f.inv.rt. Our alpha is 0.05. We do not divide by 2 for a one-tailed test. Degrees of freedom of the numerator, remember our second group was in the numerator. Degrees of freedom of the denominator, our first group was in the denominator. Similarly, we'll use the f.dist.rt function for the p-value. The first argument is the calculated value, and then the degrees of freedom of the numerator and the degrees of freedom of the denominator. We do not need to multiply this p-value by 2. Comparing f-calc to f-crit, we see that f-calc is now more extreme than f-crit. This tells us to reject the null hypothesis. Additionally, our p-value is less than alpha 0.05, which also indicates we should reject the null hypothesis. That is our statistical conclusion. Our biological conclusion for this problem comes from the hypotheses. Since we reject the null, this means in a way that we accept the alternative, that the variance of group 1, being the shallow reef, is less than the variance of group 2. These are variances in body length, so our biological conclusion will be that the variance for body length of fish in shallow reef is significantly less than, because of our p-value, that of fish in deep reefs. The problem in the book goes a little bit further in talking about competitors and things like that, but because we're not all ecologists, that level of detail will not be required for the exam. Now that we've done this work in Excel, and it wasn't too bad, let's move into R, because this was quite easy, but in R it is even easier. The first thing we need to do is open R and make a new script. So we'll go to File, New File, R script, and we'll get that fourth panel open here. We need to save our data in a column format. So this data already has For question 1, nice columns, I'm going to copy both of those columns with the column names. I'm going to open a new Excel file and paste it in. And that looks good. The data is in column format. We have our first group in the first column, our second group in the second column. So this is perfectly good to go ahead and save. I'm going to save this to my desktop. And this data is about body weight, percent deviation. I'm going to call it body weight. And remember, R only likes working with CSV files. So save as a regular CSV. Press save. If you get this error, it only asks if we are sure we want to use a CSV, and we are, so we hit yes. Back in R, we need to tell R where it can find our data. So we will go to Session, Set Working Directory, and choose the directory. My data is stored on my desktop in my desktop folder, so I will open that folder. Now we need to load in the data and save it to a variable. I'm just going to call this variable Q1 for question 1 from this chapter. We use the arrow sign to assign data to a variable. We're going to read the CSV, so read.csv. And I called my data body weight. You can either type that in or just start typing and press tab, and the rest of it should autofill. Our data does have column names, so we need to tell R that it has a header. So we set header to true. To run this line of code, we either press run or hit Control Enter on your keyboard. You should see down here, the code successfully ran and no data printed because all we did was assign this data to a variable. The next thing we always want to do in R is look at the data we just imported. So we're going to use the function head with the variable we assigned it to, Q1, and that's a capital Q. Run that line, and we see 2 columns of data. Again, if you see other columns that maybe say NA or have some different numbers in it, you may need to go back to your CSV file, delete columns, using the selection of the columns, clicking up here and clicking delete sheet columns. You need to save the file again, go back into R, and you will need to rerun lines 1 and 2 to see that change. Now that we know our data is good to go, let's go ahead and run the F-test. To run the F-test, we'll use the function var.test. There are 2 arguments for the var.test function, and these are the data that we'll be comparing the variances for. In the previous version of this video, I misspoke slightly and said that the order of the arguments doesn't matter. And this is true for the p-value, but the order of the arguments does matter for the fcalc value, and I'll demonstrate that here. First, we'll just start with the data, and we'll use data Q1 with the healthy individuals and the data Q1 from the cancer individuals. When we run the F-test, we take a look at the output, and first thing, let's just look at the p-value is 0.1875, telling us to accept the null hypothesis. Then let's look at the fcalc value here, as well as the ratio of variances, and these should match. And since we always want the F-test to be a right-tailed test, we should expect these ratios to be greater than 1. If they are not greater than 1, that means we need to switch the order of the arguments in the var.test function. So let's do that here in line 4. Now we'll do var.test with Q1 cancer and Q1 healthy. And I ran that command, and we see that the p-value is the same, but the fcalc value is now greater than 1. This would be the correct order of the arguments for the F-test. So just to reiterate, the order of the arguments in the var.test function does not matter when we're looking at the p-value and deciding whether to reject or accept the null hypothesis based on that. However, the order does matter when looking at the fcalc value, and do make sure the fcalc value is greater than 1. Finally, looking at the p-value and the fcalc value for this question, both of them indicate that we should accept the null hypothesis that the variances of these two groups are equal. Let's go ahead and start working on question 2 from this chapter. First, I'll open up the chapter 12 template to see the data. And I don't like the column names here, and they're also merged in this document. So I'm going to go ahead and just copy the numbers themselves. And I'm going to copy them into the same body weight CSV file so that I only have to save one file for all the data from this chapter. Before pasting it over here, I am going to paste it just a little bit to the side so I can make my own column names. The first set of data was from the shallow reef, so I'll go ahead and type that here. And I'm going to cut and paste the numbers for that data into that column. I'll do the same thing for the deep reef data. Again, cutting and pasting this data into one column. Just to be sure that there's no remaining data or formatting in any of these columns, I'm going to select all these columns and just be safe, highlight more than I actually need to, and then go to delete and delete sheet columns. This should get rid of anything that may show up when we look at this data in R. I am going to save this file and say, yes, that's no problem using the CSV format. Going back into R doesn't know that we changed this data, so we have to rerun lines 1 and 2. So I will run line 1, telling R which data to import, and rerun line 2, and we can see that the data output is different than what we had before. We not only have the healthy and cancer data, we now have the shallow reef and deep reef data. So let's go ahead and run the f-test with this data. I'll space down just a little bit, and we're going to use the same test, var.test. We're still calling this data Q1, but now we're using the columns shallow reef and also from Q1 deep reef. Running this test, let's take a look at the fcalc value and the p-value. So first of all, the fcalc value is less than 1. That indicates to us that the arguments need to be switched so that the column with the greater variance will be used in the numerator of this calculation. Remember that the p-value will be the same either way. But let's go ahead and change line 6. I'm going to change the first argument to deep reef and the second argument to shallow reef. Running that test, we see the same p-value as before, but now we have an fcalc value and a ratio of variances that is greater than 1. Using these, we can use the degrees of freedom from the numerator and the denominator in Excel or in the statistical tables to find the f-critical value. In this problem, the p-value is 0.001569, which is less than our alpha of 0.05, telling us to reject the null hypothesis. So we would conclude that the variances in this problem are not equal. The last thing we'll do in this video is go ahead and save this file. And I'm going to continue working on my desktop, and this file I'll call Chapter 12 F-Test. We don't change the file type, press save, and that's it. That will conclude our video for the F-Test.